Okay, thank you. It's a pleasure and an honor to be here in this conference. I still remember very well the first time I met Russ, but maybe that shouldn't be very surprising since it was just 3 days ago. Okay, so I'm going to tell you about a condition for long-range order in discrete spin systems. Let me first tell you what the setup is. So we have a finite set S, which we think of as our spins. And we have positive numbers, lambda I, for every I in S. And these we think of as single site weights. And for every pair of spins, of values in S, we have a symmetric non-negative number, which we think of as the pairwise interactions. Okay, and this defines for us a spin system in the sense that we will consider functions from ZD to S. We'll call these configurations, and the probability of a given configuration is going to be proportional, so just up to some normalizing constant, to the product over all vertices in our graph of the single site weights, times the product over all nearest neighbor pairs, over all edges in the graph of these pairwise interactions. Okay, and for those of you who haven't seen this before, you may ask whether this is well defined, and as I wrote it, it's not. And the usual thing to do is, one usually considers, say, a box or something, or any finite set, omega in ZD, so some finite set. And then here, this should be, so this is the formal way to do things. You replace this by this finite set, and here the vertices, the product is over vertices in omega and edges in omega. Okay, now since everything is finite, there's just a finite number of configurations, and this is well defined. Okay, so you may know a lot of classical models, spin systems which fall into this setup. The Ising model, the Potts model, maybe less well known, the hardcore model, or Widom-Rowlinson. No, I just mean otherwise this is an infinite product. And
but the P is not uniquely defined by this proportionality.
Okay, so let me say something about boundary conditions. Usually one imposes some boundary conditions, either fixed or periodic, and what I described here are the free boundary conditions. Okay, but
so what is the free boundary condition?
It's this. So it just means that there's, in a sense, no boundary conditions. It's exactly this. Okay? So the vertices on the boundary don't interact with anyone outside. Okay, so it's rather classical in these types of models that there is disorder in some cases, or if you wish, uniqueness of the Gibbs measure. So in the infinite volume limit, things aren't always unique, but there are conditions for uniqueness. And let me just to state too, there's Dubruchin's uniqueness condition. It's from 1968. And there's also condition by Vandenberg, kind of disagreement percolation from 1993. And there are also other types of conditions. But this is not the goal of the talk. The goal of the talk is to describe when there is order.
But just returning to Ben's question, something is still, and you can define it a little more correctly.
Okay. So,
because this is on a finite set, but these measures are not consistent between different sets. So, are you taking limits?
just defined on a specific omega. For any omega, this is well defined. Okay?
You forgot about ZD.
I forgot about ZD. I'm just thinking.
I'm not going to go back.
I'm just thinking of a large box, but everything I'm going to say is going to be independent of omega, or this is what I'm aiming for.
Uniqueness of what?
Uniqueness when you let omega tend to ZD, then you might not have a unique limit. Okay.
So if you don't have uniqueness, there are serious measurable issues about choosing a Gibbs measure.
That's right, and this is what the talk is about. So So this is the goal. But I don't want to talk about this technical things. That's why I'm always going to stay in a finite region, and I'm going to explain all the results in a finite, the finite version of the results, but these extend to, these say something about the infinite volume limits. Okay? So our goal here is to understand when there is long-range order. And specifically to find a general condition for when there's long-range order, since many specific models, like the Ising model, the Potts model, and things like this, already there are, people know how to prove that there's long-range order, but we're looking for something general. And just to say once again, since we started talking about infinite volume measures, this is kind of the same as asking whether there are multiple infinite volume measures, something that's called usually Gib states. Okay? So what type of order should we expect in these kind of models? Well, ZD is bipartite. So it has a type of chessboard pattern to it. And as it turns out, these are the type of orders which will appear. So the type of long-range order that we're going to see arising, you have two subsets A and B of the spins of S. And what we're going to see, so this is kind of just a impressionistic picture. And what I mean by this is that this guy has some value in A, this guy has some value in B, this guy has some value in A, and this continues, well, in this picture everywhere, but we'll see in a moment what the precise result is. This is what we're aiming for. Okay, so we're looking for these sets A and B, which will give such an order. Okay, so to formulate our results, we're going to need a few definitions. Well, two definitions. The first, let us call a pair of AB, of subsets of S, a phase, if gamma AB is maximal for all A and all B and B. Okay, what do I mean by maximal? I mean that it just equals the largest pairwise interaction in the system. Okay, so I go over all the pairwise interactions, over all ij, and I want all the gamma ABs to be this maximal value. Okay, so this will be a phase. And what is the meaning of this phase? It means that if you look at this picture where all the even vertices have A, so let's say the A's are on the even vertices and the B's are on the odd vertices of ZD, well, it means that any two neighbors, no matter what value of A is here and what value of B is here, little a and little b, their interaction is always the largest possible. So it gives the largest contribution to this factor. Okay, so this seems relevant. And we'll see in a moment what role this has. But not all phases have the same weight. Okay, if you look at two different phases and consider what weight these configurations give, some give larger weight, some give smaller weight. And so another definition to look at, which makes sense, is to say that a phase AB, let's call it dominant. So phase AB is dominant if lambda A times lambda B is maximal. So what is lambda A and lambda B? So for a subset of S, I define lambda I just to be the sum over these single site weight. And then maximal just, I mean, it's the maximal possible product over all phases. Okay, so no, they don't have to be disjoint. Yes, because gamma II could be maximal. So if gamma II is maximal, then there's no problem to have. So gamma AA could be maximal.
So I see. So you're allowed loops. That's what you're saying.
Yes. Exactly. Okay. So they could even be equal. Okay. It might. We'll see. Okay. I don't know if I'll discuss examples, but if you have in mind the Ising model or the ferromagnetic Potts model, then A and B are actually going to be equal. Okay. So.
I don't understand
you move gamma II to lambda I? I mean, can't you assume gamma II is 0?
No, you could assume that lambda I may be all equal. You can move this to here, but not the other way around. And even if you can assume some things, just play with it however you want, and then take these definitions. And actually, this is a good point. Sometimes sometimes moving the weight from one to another changes the definitions, and then the results may or may not apply.
Is there a lambda II? Is there a gamma II?
Did I write somewhere?
Is U a neighbor of itself? The graph in ZD, is U a neighbor of itself?
No, it's not a question of if U is a neighbor of itself. It's a question of whether the vertices in S are neighbors of themselves. Okay? A and B are subsets of S. Okay? So these are subsets of spins which sit on the even and odd vertices. Okay, and it might be that the spins sit both on the evens and on the odds. Okay? Okay, so these are the definitions we need. So before I formulate our results don't apply to every spin system. We need some assumptions. So we're going to have two assumptions. And the first assumption is an assumption of symmetry. Okay, so the assumption is that all dominant phases are symmetry of dominant phases. Okay, and what does this mean? It just means that for any two dominant phases, A, B, and A prime, B prime, there exists a weight-preserving bijection of the spin space. Weight-preserving here just means that lambda of phi I equals lambda I, and gamma of phi I phi j equals gamma of ij for any I and j. Okay, so it's a bijection of the spin space which preserves these weights. So for any two dominant phases, there exists such a weight-preserving bijection which maps one dominant phase to the other. Okay, so phi A equals A prime, and phi B equals B prime. But I also allow this, it's also okay if this phi reverses the roles. Okay, inverts the roles of A and B. So it's also okay if it maps A to B prime and B to A prime. Okay, so in this sense, any two dominant phases are equivalent. Okay? So this is the first assumption. This is an assumption. Okay? The symmetry of the dominant phases. Okay, for the second assumption, I'm going to need some definitions. Before I give the definitions and write the assumption, let me just point your attention again to this fact of disorder. Okay, so in some cases there is disorder. There's no long-range order. When does this happen? It happens, for instance, when the interactions are weak. Okay, if these gamma ij's, if they're essentially equal to each other, or almost equal, then this factor is almost constant for any two configurations, and you get something which is almost independent. Spins are almost independent, and this can be formulated formally, and these are the results of de Bruch and Vandenberg. So even in the Ising model, to have order, you need to take the temperature to be low, right? Only at low temperatures you have some order. So now I want to state this to quantify how low the temperature should be in some sense. Okay, or in different words, how dominant are these dominant phases? Okay, so I just defined that a phase is dominant if it maximizes this guy, but it should be very dominant or sufficiently dominant in order to have long-range order. Okay, so for this I'll need a few quantities. Let me denote by P gap, P for phase. So the gap in the phases. So this is just the ratio between the largest weight of a phase, that is the weight of a dominant phase, and the weight of the next phase, okay, of the next subdominant phase. So maximum over all A, B, which are phases, but which are not dominant. Okay, so this is a quantity which is always strictly greater than 1. The larger it is, the larger the gap is. And then there's a similar gap in the pairwise interaction. So this is the ratio between the largest pairwise interaction, which we called gamma max. Okay, this guy. And the next largest interaction. So the maximum over all ij, such that gamma ij is not equal to the maximum of lambda of gamma ij. Okay, and again, by definition, this is strictly greater than 1. Okay, and we'll need two other quantities which, for some technical reasons, so the ratio between the largest and smallest single site weights, and let me also denote the number of spins by Q, okay, the size of the spin space. Okay, then the second condition, let me put it here. So the second condition is an inequality which quantifies how large the gap is. Okay, so informally, I want there to be a large gap. So how large? Okay, I hope this won't terrify you, but so there is some inequality. This is the only thing that's really going to be important. There's some explicit inequality. Okay, and I want to point out two things, or three things. First of all, it's an explicit condition that one can check. Everything here is explicit, except for this universal constant, which you could take probably to be 1 million, or something like this. But other than that, everything here is explicit. And, yeah? A universal constant, 1 million, or something like this.
Left-hand side.
Okay?
C on the left is the same as C on the right?
No, C on the left is a small constant, 1 over 1 million. Okay? Sorry. Yes, okay. So all constants are universal whenever I write a constant. Okay, so two features of this which will be important, or which I want to draw your attention to.
You know, and Q is the cardinality of S.
Yes. Okay. So two features of this inequality. Again, you don't really need to understand the inequality. Just two features to note is, first of all, for any dimension, no matter what d is, if these gaps tend to infinity, then the left-hand side tends to infinity. And as long as I have some minor control over this q and delta, then the condition will hold. Okay, so for any d, A2 holds when p gap and gamma gap tend to infinity. That is when they're large enough. Okay, and this is what one usually does in the Ising model. One takes the temperature to be low, and this controls, for instance, the gamma gap. So as the temperature tends to 0, the gamma gap tends to infinity, and this is how you recover results for the Ising, for instance. The second feature which I'd like to point out is that for fixed weights, that is for fixed lambda I and gamma ij, well, the left-hand side is some positive constant, since we said that p gap and gamma gap are strictly greater than 1. This is some positive number, and when d tends to infinity, this goes to 0. So for fixed weights, no matter what they are, A2 holds in large when the dimension is sufficiently large. So let me write this as d tends to infinity. Okay, and this is the main kind of important new feature, that no matter what the weights are, if the dimension is large, then A2 holds. So we have another extra parameter, the dimension, which a lot of times doesn't come into play, in typically at least. Okay, so now I can state the results, unless there are any questions.
Are you going to give some examples?
Yes. So right after the results, I'll explain the results in the context of two examples. Okay, so here are the results. Just before I state the result, let me give one small other definition. Let's say that a vertex of ZD is in the AB phase if it satisfies this kind of pattern. So if it belongs, if f of u is a when u is even, or f of v is in b when v is odd. Okay, so just that it actually conforms to this AB pattern. Okay, we'll say that the vertex is in the AB phase. Okay, so here's the theorem. Suppose that A1 and A2 hold. Then, for any dominant phase, for any finite omega, this was the box where the model was defined on, and for any vertex in omega, the probability that V is in the AB phase, condition that the boundary of omega is in the AB phase, is at least, say, 0.99. Okay, so what this is telling you is that if you force the values on the boundary of a large box to be in some phase, then any vertex inside, so this is the conditioning, then any fixed vertex inside is likely to conform to this phase. And this is uniform in the size of the box. So no matter how large you take the box, you put these boundary conditions and still any fixed vertex inside is going to conform to this phase with high probability. And here the 0.99 is just depends on how large the gap is. So if you take this constant to be even larger, then you can get this number even larger. Okay? So is this clear? Okay, so we discussed a bit this issue of uniqueness of Gib states and multiple Gib states. So this, for people who know what Gib states are, this shows already that there's multiple Gib states, that any dominant phase gives rise to a Gib state with this AB ordering. But in fact, we can show that these are, in a sense, all the Gib states, or all the translation variant ones. So A1 plus A2 implies that that the periodic extreme equilibrium states, equilibrium state is just a Gib state of maximal pressure, are in bijection with the dominant phases. Okay. So for those who don't understand what this means, don't worry. This isn't going to be important. But informally, it means that the only possible orderings that you can see are what come from the dominant phases. No other type of ordering can occur. Okay, so this classifies all the types of ordering which you see under these conditions. Let me just remark that the theorems hold with ZD replaced. So you don't actually have to work in high dimension. You can work in low dimension, in any dimension, in fact, at least 2, as long as you enhance the degree locally. So for instance, like this. Okay, so globally it's 2-dimensional, but locally the degree is high, and still all the results hold. Yeah, the D is the same. So you need the sum of these to be large, and you need it to be at least 2-dimensional globally. Okay, so let me come back to some examples. So I mentioned a few well-known examples like the Ising and the Potts model, or the ferromagnetic Potts model. Let me not discuss these, since these perhaps are better known. Let me instead discuss 2 examples where our results give new new results. In the other cases, our theorems apply as well, but they recover previously known results. Okay, so the first model I'd like to discuss is the Widom-Rowlinson model. So graphically, I can. So when I mean model, I'm just defining now the spin space S and the interactions, the lambdas and the gammas. Graphically, I can represent this as follows. I'll explain in a moment what this means. So the edges, it's a graph, and the edges, the vertices are the spin values. So S is minus, 0, and plus. An edge corresponds to whether an interaction is allowed or not. Okay, so it means that the gamma ij's are 0 if I and j is plus and minus. Okay, there's no edge between plus and minus, and otherwise it's allowed, and with no weight, just 1. Okay, so this is the gamma ij's, and the lambda i's are going to be lambda here, and 1 here. Okay, so lambda I is lambda if I equals plus or minus, and 1 if I is 0. Okay? So here, let me first discuss the case of disorder, of uniqueness. So using these general conditions I wrote before, de Bruchen's uniqueness condition, for instance, one can see that there is a disorder or uniqueness when this lambda is less than some universal constant divided by d. Okay? And how should you think of this? This intuitively makes sense, at least that when lambda is sufficiently small that there is disorder, because lambda is the weight of, to see a minus or a plus, and if this is small, then essentially you'll only see zeros. Okay, so almost everywhere you see zeros, and just here and there you see plus and minus, so things are disordered. Okay, so let me discuss now the other side, the ordering. Okay, so for this we want to understand first what the dominant phases are, because the theorems tell us that these are what will give us the order. So what are the dominant phases here? Well, the only thing that's not allowed when I choose my A and B is to have to have this minus in one side and the plus in the other side. That's the only thing that's not allowed by these pairwise interactions. And just checking this, one can check that the phases are minus and 0 on both sides, and similarly plus and 0 on both sides. Okay, these are the dominant phases. What ordering does this dominant phase correspond to? It means that most vertices, well, since the A and B are equal, it just means that most vertices are either plus or 0. Okay, and it's very rare to see minuses. And this one, it's exactly opposite. Most vertices are 0 or minus. Okay, so let's try to quantify this. So there's order. This was a known result, that there's order in when lambda is sufficiently large. How large? Exponentially large in the dimension. And this is a result which goes back to Lebowitz and Gallavotti from 71, and to Burton and Steif from 95, who were the first to introduce these kinds of models in the context of ergodic theory and as examples of subshifts of finite type with multiple measures of maximal entropy. Our result improves this bound. So you see that there's a very large gap between the unique or disordered regime and the ordered regime. This is exponentially large bound. And actually we showed that there's uniqueness even when lambda tends to 0. And in fact, we don't recover the correct polynomial, the correct power. So thank you. But we do show that it at least tends to 0. So lambda needs to be large, but as the dimension increases, large is actually not so large. Okay, it can even tend to 0 with the dimension. and still you have order. Okay, any questions? Okay, then let me move on to the second example. This is the example of the anti-ferromagnetic Potts model, or if you will, proper colorings. This is also a very simple model, so the spin space is just the numbers 1 up to q. All of the single site weights are 1, and the pairwise interactions are 1 if I is different than j, and if I equals j, then it's some e to the minus beta, where beta is some positive number. This is the inverse temperature. Okay, for instance, when beta equals infinity, then this is 0. And then the only restriction is that you're not allowed to have, if we think of these as colors, then 2 neighboring sites on ZD cannot have the same color. Besides that, all configurations have the same weight. So it just means that we're sampling uniformly a proper coloring.
Can you repeat again what is the result for the previous model precisely?
This order, yes. So let's look at this result, for instance. So it tells you that if you put on the boundary of a large box, you put this, say, this boundary condition. So, okay, let me write it as plus, although it's plus or 0. Okay, then any vertex inside is not likely to be a minus, very not likely to be a minus. It's either a plus or a 0. Okay, and of course, if you would put the minus 1, then you would see a minus inside.
This is what is this numerical relation lambda that you see?
This is how large lambda should be to have this behavior. When lambda is small, you don't have this behavior. Okay.
I want to understand the logic. So this is a consequence of the theorem we quoted before?
Yes, it's this theorem. So
this inequality comes from A2?
yes, sorry. So I didn't want to do the computations here, but once you have, yes, in principle, once you have these, you can compute all this p gap and the gamma gap and the delta and everything and plug it in, and you get this condition. Okay, it's a very simple computation, but there's no, I don't want to do it here. Okay, and the same thing is going to happen now with this example.
Can I ask one question? In that theorem, you can put any guy from the A, B phase on the boundary?
No, not any fixed guy. What I'm doing is just conditioning that. So I'm not telling you what value of A or B is on the boundary.
You're doing the free and then you're conditioning.
Yes. I'm just conditioning that the value that you see there belongs to A, not telling you which value.
So why did you put pluses there?
I said it just so that I won't have to do this. It's plus or 0. Okay? Okay. So let's again look at when you have a disorder. And again, from the same conditions that, same general theorems I stated before, de Bruchen's uniqueness condition, one can show that there's uniqueness when the number of colors is sufficiently large. Large here just means some constant times the dimension. Okay, this constant isn't even large, it's 4 or something. So once you have 4 times the number of the dimension, which means twice the number of neighbors, then you're going to be disordered. Okay? And the question is, what happens when in the opposite regime? So there's a conjecture by Kotecký from 85. He conjectured that there's order when the dimension is sufficiently large as a function of the number of colors, and beta is large as well. Okay, which means the opposite condition, where instead of the number of colors being large in comparison to the dimension is large in comparison to the number of colors. Okay, so what type of ordering do we expect? Let's quickly look at what the dominant phases are here. So again, dominant phases means 2 subsets which maximize this quantity, meaning that anything in A cannot be in B. Now they have to be disjoint because of this thing, and if you want to maximize the product of the weights, then you want to equally split the colors. Okay, so the dominant phases will look like this: 1 up to Q over 2, and Q over 2 plus 1 up to Q, and the permutations. Okay, and any permutation of these colors. So there's a lot of dominant phases. Okay. So when do we have order? What is the condition? So for Q equals 3, this was previously known. This is due to Ron, and independently to Galvin, Kahn, Randall, and Sorkin from 2012. And they did the case of beta equals infinity. And the case of finite beta was done by Ohad Feldheim, who's sitting here, and myself. This was last year, but published this year. This is the case of beta finite but large. But let me point out that the case of Q equals 3 has a special structure to it. For instance, this manifests itself, for instance, in the case of proper colorings. When beta equals infinity, there's actually a height function representation. For finite beta, this height function representation breaks down, but still there's some special structure to this Q equals 3. In particular, the case of Q greater or equal than 4 was completely open until now. And our results show that there is order. Indeed, when the dimension is sufficiently large, how large? It needs to be polynomially large in the number of colors. And again, beta also should be large. But similarly to before, it's not so large. So it needs to be large, but actually it's allowed to tend to 0 with the dimension. Okay, so it means that the critical temperature of this anti-ferromagnetic Potts model tends to infinity as the dimension tends to infinity. Okay, so again, let me explain what this means ordering. It means that if you take a box, for instance, let's look at 5 colorings, okay, and you take, for instance, the dominant phase 1, 2, and 3, 4, 5, and you condition that the even guys belong to 1, 2, the odd guys belong to 3, 4, 5, and you do this everywhere, then any vertex inside is very likely to satisfy this as well. If it's even, it's going to be 1 or 2, and if it's odd, it's 3, 4, or 5. Okay, so I have, how long? 7 minutes. Okay, so in the remaining time, I'd like to explain to you some of the ideas of the proof. Very quickly. So in a high level, this is some type of Peyers argument. Okay, let me quickly remind what this means, for instance, in the case of easing. So in easing, what you do, you have, say, plus boundary conditions. Then you find the contours inside, which separate pluses from minuses. And then the idea is to explain why such a contour is unlikely. Well, in the easing model, it's unlikely because there's an energetic cost on the boundary. Okay, every time you have a plus next to a minus, it costs you something. If you flip all the spins inside, you gain this energy. So the probability of a contour is small. And if the temperature is sufficiently small, then you can make this probability very small, small enough to combat the number of contours. And then you just do a union bound and you're done. So this is the general idea. However, there are some complications. And let me explain this in the case, for instance, of proper 5 colorings. The ideas already, essentially all the ideas appear here. So what are the complications that arise? Well, the first thing is that it's unclear how to even define these contours. Specifically, how do you answer the question, what is the phase of a vertex? Why is this unclear? Well, in the easing model, if you look at a vertex and you see it's a plus, well, what phase does it belong to? It's trivial that it belongs to the plus phase. There's no question about it. But in 5 colorings, if you see a vertex and its value is 1, then what phase does it belong to? Does it belong to the 1, 2, 3, 4, 5 phase? Or maybe it belongs to the 1, 5, 2, 3, 4 phase? There are many choices. So you have to somehow decide which phase it belongs to, just to even have a picture of contours. And the idea is to look at the neighbors of this guy. Okay, so for instance, if you see these values, 2, 4, and 5 on the neighbors, well, the neighbors actually tell you what the phase is. It tells you that there's 2, 4, and 5 on the neighbors, and then you kind of infer that that you're in this phase. Okay, but this gives rise to other complications. For instance, it might be that you see on your neighbors 2, 3, 4, and 5. Well, this doesn't give rise to any phase because there's 4 values. Okay, so this I will call is somehow bad. It means that there's no phase that I can associate it to. But also the opposite thing can happen. I can, for instance, see all 2s around me. And then, again, it's not uniquely defined. I belong to a lot of phases. Okay, so I might be in some kind of overlap between the phases. So the picture you should have in mind, instead of this naive picture of one contour, the world kind of splits. So I put some phase on the boundary, which I'll denote by I, and the world kind of splits. This is still just an impressionistic picture. But say this belongs to phase 2, this to phase 3. This may be in the overlap. So it's in both the phase 2 and phase 3. And maybe this is bad. It doesn't belong to any phase. Okay? The second complication is that there's no energetic cost to boundaries. That is, on the boundary between phases, you don't lose any energy. Why not? Because, well, all configurations have the same probability, so there's nothing to play with. Instead, you lose entropy. And this, for instance, just let's look at this kind of picture, which, okay, I hope maybe you can understand what this means without me explaining too much. But this is supposed to show an interface between 2 phases, the 1, 2, 3, 4, 5 phase, and the 3, 4, 1, 2, 5 phase. And if you think about this, there is some loss of entropy here, because instead of having every other vertex have 3 choices, there's 2 vertices next to each other which only have 2 choices. Okay, and the way to kind of work with these is to use entropy methods. And with this, I'll just say the third complication. So the idea is to use entropy method. Let me just say the third thing very quickly. The third complication is that there are too many contours, by which I mean that here we said that we can take in the easing the temperature sufficiently low so that the probability becomes so small that you can combat the number of contours. Well, here there's no parameter to play with. The probability of some contour is what it is, and there's no external parameter to play with, and you cannot combat the number of contours. It can really be shown that there are too many contours, and then the idea is to use the dimension as the extra parameter, to take the dimension sufficiently large so that the gaps become large in the sense of this A2 that I wrote before, and still one needs to do other things, needs to approximate these contours. You still can't count them, and some complications here arise, but I don't have time to get into this.
You had precisely the right time to convince us that this is completely hopeless.
But it's not. So is that a question? I can answer that. I get a few more minutes. Okay, so the idea is that in high dimension, you can kind of approximate contours. Okay, so by which I mean that there exists a small family, but small here is now as d tends to infinity. So here you use the high dimension, a small family in parameter d.
So for 5 coloring, it only works for high dimensions?
Yes.
And it's not true for small dimensions?
It's not. For 5 colorings in 2 dimensions, it's still open. But for instance, 7 colorings in 5 dimensions, in 2 dimensions, it's known not to work. And specifically in any dimension you give me, if there are enough colors, there's no way it can work. This is known. So there's no order. So the dimension really needs to be large for this to work. Okay, and the idea is that if the dimension is large, you can find a small family of skeletons of the contours. Okay, sure. Okay, so these entropy methods, specifically, this is Shearer's inequality. It's an inequality from information theory. It was first used or pioneered by Jifcon in works on the hardcore model. But this has been used quite a bit before, but always in the case of finite graphs. So for instance, on a finite torus, on a hypercube. And this is the first place that it's kind of been adapted to ZD and used for a graph with a boundary, if you will. Thank you.